Hello, hello. Hello to all. Hello to all. Welcome to this last session of this ISF 24 conference in Dijon. As we say, as usual, last but not least, for sure. So we have the chance to have with us il professore Tommaso Proietti from the University Tor Vergata in Rome. So Tommaso is going to be our last speaker of the conference, last keynote speaker. And just to remind you, that in the wake of his presentation, we will have a closing ceremony. So if you want to stay with us, that would be fantastic. So Tommaso, no need to present Tommaso, but Tommaso is professor at University of Tor Vergata in Rome, and also a research associate in Aarhus in Denmark at Proietti. Tommaso is a statistician, and I know Tommaso for many years, so Tommaso is really amazing. As soon as you have a question on anything, you can be sure that Tommaso is likely to provide the answer. So Tommaso is specialized in time series econometrics, time series forecasting, statistical model, etc., etc. And today, Tommaso is going to talk about something that I like, turning points, and how to measure turning points and to anticipate turning points. We know that it's not an easy job, but I'm sure that we will learn a lot with you. Welcome, Tommaso. Happy to have you here.
Well, thank you very much, Laurent, for this very kind introduction, and thank you to the organizer for having me here. It's a great conference. It's a beautiful place, and thank you all for being with me today. So this presentation is about essentially the analysis of some issues in economic time series mostly, and financial time series. And just let me start with providing some motivation. Here you see the stock exchange index in Paris for the last few months. That's the last observation available to me. That's the 28th of June, so 1 week ago, before the elections. And many times we ask questions in economics and finance, such as what is a measure of that is representative at time t, at the last time available time of the series. And so there are many feature extraction filters that can address this question depending on the research question that you ask. So some people would be happy with reporting the last observed value, which is a measure of tendency, say, under a random walk assumption or under the efficient market hypothesis. And it's also called in forecasting the naive forecast. Traders would look at a moving average, an unweighted moving average of the last 20 observations, for instance. And if this was an output time series, such as GDP or industrial production, people would look at measures of trends, assessment of trends, and cyclical stance, which is a deviation from trends. So when you want to extract features from this time series, you essentially use the last available observation and a number of past observations, and you use a filter to extract features that may be relevant. Here is a list of what people are doing. Among these things, I perhaps forgot to mention dating turning points of the series, which is a very, very popular thing that is done. And perhaps I should mention also the Brian-Boschen filters and so on and so forth. Now, what I will be doing is to look at a class of filters, you may call it a nonlinear filters, or that look at the running maximum and minimum of a time series. So for instance, if we go back to the CIC index, the run-in maximum for the last 22 observations would be located here. Is the dashed line, right? So at this point, you were at the maximum of the last 22 days, and then you see the maximum stayed stable here. Then it went down just because the 22 days before you were going down. And I will look also at the minimum of the time series. This is the run-in minimum of 22 consecutive observations. And I'm going to argue that you may extract interesting features from this simple measurement, right? Very simple measurement. In particular, if you consider the time that has elapsed since you were at the maximum and at the minimum, then you can generate a multinomial process, which actually represents a Markov chain. And under certain assumption about the underlying process, this Markov chain is informative about several features of the time series, such as the reversibility. And you can use these chains to date the business cycle. So you could provide the division in the characterization of phases of the market, expansion, recessions, bear and bull markets in finance, and so on and so forth. So this this measurement framework turns out to be both simple but also informative on several research questions that we ask. So this is what I will talk about. I will start with some definitions. I will define the run-in maxima and minima and the gaps that are associated with it. And I will provide a definition of this Markov chain that is used for further investigation. And then I will look at some applications. So mostly I will be looking at applications. One application is the analysis of time reversibility of economic time series. Another thing I will do is measuring output gaps. This will be referred to economic time series of output such as GDP or industrial production. Then I will consider the problem of dating turning points, peaks and troughs of the market, say of a financial market, and the distinction between bear and bull phases. It can be seen that an algorithm can be based on this measurement to provide such dates. Finally, I will conclude with a prediction of the drawdowns. The drawdown is a measure of potential loss that you incur when the current price of an asset is below its current maximum. So that's some relevance in finance, and you can characterize the properties of drawdowns within this measurement framework as well. My talk is based on 3 papers, one published, 2 at the stage of working papers that I can make available. Right, so just to put the things into the framework, there is a substantial literature on the things I'm talking about, much more than is represented here. You know, my starting point, my motivation started a long time ago when I was looking at this paper. So we were in the other century, and I was looking at this paper, the current depth of recession, which is a measure of how deep is a recession that is used for, it has some predictive value, which is shown in this paper. And since then, you know, a long time has gone, and when I looked again at this problem, I sort of thought I could contribute to it. Now, as I said, in finance, there is large literature on the drawdown, and this is a measure of risk, essentially, that plays a role for risk assessment and also for portfolio management and construction. Here is just a list of reference. Gebert's is a review paper in the Journal of Economic Surveys. Now, coming to the applications, in time series analysis, you have a lot of, for instance, for testing reversibility is a problem that has been studied for a long time. You see earlier references are Tong, Lawrence, There is a long tradition in dating market phases, dating recessions and expansions. Of course, you have Brian Boshen here and all the related literature, Zarnovitz and so forth. So this is just underrepresentation of huge literature there. And from the statistical point of view, you have this thick band transformation, which is a sort of a geometrical view on these filters. It's an interesting paper on the JS Journal of the Royal Statistical Society, Series B. The max and mean filters are used also in image processing. And you have a lot of literature in applied probability for, it's called the fluctuation theory of partial sums of random variables, the duration of rallies of processes, and so on and so forth. So there is a huge literature that is also related to what I will be doing. Okay, some definitions first. I will be concerned with a time series process, YT, which is typically the logarithm of output or the logarithm of price, of portfolio value or price. Of course, I will denote the change in value by delta YT. That's the first differences. This is one period change. T is time, will be regular time, so this time will be discrete, can be in days for financial time series, can be in quarters, months, and so forth. So delta YT is going to be my first difference, and the delta I YT is going to be the difference with respect to an horizon of I periods. So it is ith period difference, the ith period change, which of course can be expressed as the accumulation of the first differences of the process. And for convention, I will denote with 0 is delta 0 YT. Okay, the first definition deals with the maximum or the tau maximum of a time series or a stochastic process. Tau will be a positive integer, which I will assume to be fixed. And the tau maximum process will be denoted by MT plus. There will be a plus on top. And is essentially the run-in maximum. You see this is a filter applied to the current value and the tau plus value. So you consider a run of tau plus 1 observations, and you locate the maximum. That's called MT plus. And the associated gap max process is denoted by GT plus, and is the deviation of the current value from the maximum. Right? So that's a negative value. If you change the sign, you get what is called in finance the drawdown, right? Is the loss that you have when the current price is below the running maximum. And the lead time with respect to the running maximum is the process ST plus, right? So this process takes values I can be 0, 1, and so on and so forth. If you are in state 0, it means that you are at the maximum at time t. So the running maximum coincides with YT. If ST plus is equal to 1, then the running maximum was 1 observation before, and so on and so forth. So you have a multinomial random variable taking tau plus 1 values, right? So that's the lead time with respect to the running maximum. Of course, you can have similar definitions for the running minimum. The running minimum is the minimum of this sequence of consecutive observations. That's denoted by MT minus. And the gap with respect to it, now it will be a positive value or non-negative, will be YT minus MT minus. In finance, this GT minus is known as the draw up, right? And also in this case, we can define a variable, ST minus, denoting the lead time with respect to the running minimum, right? Again, you have a variable that takes value 0 if the minimum is at time t. It takes value 1 if it's the day before, and so on and so forth. Another definition is the following that I will use, the gap process. The gap process is the average of the gap mean and the gap max once you have removed the average of the two, right? So that's expressed in deviation form from the mean. We will see that under certain conditions, this mean is stable, right? It's fixed, right? And so you see we have defined the gap max, the gap mean. We take an average and we remove the average of this variable here. Now everything here will depend on tau. Tau will be an integer, and it denotes an horizon. You can call it a bandwidth, right? So that's important, and I will take it as fixed. Just as an illustration, here we have the dotted line here is the logarithm of the closing price of Standard & Poor's 500, the stock market index, right? So that's the time series, and what you see in red is the realization of the max process when you use tau equal to 22. Tau equal to 22 means that you are looking at the running maximum of a month of daily observations, right? So 22 is about a month of, so that's the horizon that you have. That's the bandwidth that you have. The running minimum is the dotted, is the dashed line in blue, right? That's the. Now, if you, of course, if you are at the last observations, right? So that's below the running maximum, which occurred here, right? So your chain ST plus is going to be in a state which is, you know, you have left the maximum a long time ago, right? A long time ago. It can be up to 22 days ago. You see, that's the state of the ST process, ST plus. And you have a deviation from the minimum. That's the gap mean. The gap mean is represented in blue here, right? You're above the minimum, and you are below the maximum. So you have a drawdown. This is the value that we use. So you have a minus gap max, which is represented here, right? When you are at the maximum, the drawdown is 0. The drawdown is 0, and so on and so forth. What you see here down below is the value of the process ST plus, the value of the process ST minus. And when you see a discontinuity, like here, for instance, this is a run of values that go from 0 down up to 22. They are discontinued just because the package that I used uses also the weekends. And so there is no trade in the weekend, so this is why you have this gap. But this is a run from 0 to 22, and it describes what you're having here. So you're below the maximum continuously. Okay, this is an illustration. If you want to look at the properties of these variables, you know, drawdowns have a lot of variability. They have high kurtosis, but they last shorter. So you see the mean drawdown is smaller than the mean draw up, right? Because the series has been drifting up. So there is a positive drift. Prices have been going up during the period that I'm considering. That year runs from the year 2000 to August 2023. So the max drawdown is 0.4, which means 40% in this case. And the maximum draw up is 25%. So there is an asymmetry in the two processes. Here you see just a snapshot for a limited time series. Yes, the drawdowns are more volatile than the draw up. And if you look at the state of the chain, the average, so the mean of the ST plus chain of variable is 8.5. So that's the average state. And it's much smaller than the average state of the lead time with respect to the running minimum. this is due to the drift, right? Essentially, you spend more time in positive states that are close to 0 in the ST plus chain. This illustration instead uses the industrial production. I'm going to look at the output gap, which is the notion of a deviation cycle in this time series. Again, you have the time series this time in black, and in blue you have the running maximum. Now with I'm using 24 months. This is a monthly time series, so I'm using evaluating these things with respect to the a bandwidth of 24 months, 2 years. As you can see, there are periods in which the maximum coincides with the observations, and the minimum is, climbing up here, little by little, and lagging behind. And there are periods in which the series coincides with the minimum, like here, big recession, right? And so on and so forth. I didn't consider here the COVID period, which I'll come back to it later. If you measure the gaps here, that's the gap max in blue. You see it's 0 often, right? 0 often. These are major recessions, In the shaded areas are the MBR recessions here. The official, say, dating of recessionary periods in which you see that you have a negative gap, essentially. And in red, you have the gap mean. When you combine the two, you get the output gap, which is in black, right? XT is this operation here that we described before, right? It's here. Yes, that's the output gap. I'm doing these things. I'm averaging those, removing the mean. That's the output gap. OK. Now, that's the measurement framework. As you've seen, that's very simple, right? Easy to program and very simple. And under certain conditions, you can characterize these processes. I mean, MT plus, MT minus, ST plus, ST minus, and the gaps are measurable transformation at time t of the series. So, and you can characterize the properties under central assumptions about the series itself. The idea is the following. It's a very simple idea. Suppose that the tau maximum occurs at time t minus I, so I days ago, or I months ago. And the time minimum is at time t minus j, so j periods ago. That's when the minimum occurred. Now, this corresponds to the value st plus equal to I and st minus equal to j, for which yt is greater than yt minus I. So the current value is, you see, it's below, right? And the current value is also above the minimum, right? So you see the gap, GT plus, will be a function of the lag I difference, right? It will be a function of the change of the process from time t to time, from time t minus I to time t. And actually, I put an absolute value to denote that the gap max is a negative value, right? Because yt is below yt minus I, so that's a negative value. I like it to denote it like this. And the gap mean would be just the change from time t minus j to time t. That's already positive. I put an absolute value for that because I like it this way. So the gap max and the gap mean are the following measurable transformation of the process at time t and its past, or if you wish, of the differences, right? So it depends. So the gap max depend on the lag I differences, delta I yt, that's multiplied by the indicator function that you are in state I, right? So you can think that the gap mean and the gap max are a function of the absolute change of the process. So they're related to volatility in a sense, which they are. They're a measure of risk in a sense. In fact, the drawdown, which is this guy with a minus sign, so that's a positive or non-negative value, it's a measure of risk. So it's a function of the absolute change of the process. So you see, that's the starting point, and the output gap is just this function of this observable function of yt through the differences, right? So through the differences. So you can analyze the properties assuming that your process is integrated of order 1, right? Integrated of order 1 means for us that the changes, the delta of the delta y is stationary. It's a stationary random variable. Now, you can extend this notion to local stationarity, because after all, what you need is that, so you see your memory is short. You're looking at a bandwidth of tau plus 1 values, consecutive values. So you can extend this notion to locally stationary processes such that the changes are locally stationary processes. But let's be more strict. I will assume that delta yt is strictly stationary with absolutely continuous marginal distribution function, which I need to avoid ties when I date the business cycle, allocate the maximum and the minima, and so forth. And I will need a mixing condition to limit the memory of the gap processes. So to avoid that the process is long memory, and to have a short memory process, I will assume something about the temporal dependence, which is not so strong after all, right? It's, we will have a weakly dependent process in the sense that it's a short memory process, which encompasses all the ARIMA processes and so forth. I'm assuming that tau is fixed. I will come back to the idea of how to choose tau, which is a key element here. Now, under these assumptions, you can have several consequences for your underlying processes. So first of all, let's look at ST plus and ST minus, which are the driving forces here. So you can show that these are first-order homogeneous Markov chains with time-invariant ergodic probabilities, which you can essentially score very simply using the differences of the process. Changes and lag changes. The story here looks difficult, but it's a very simple story. It's a very simple story. So for instance, what is the probability of being at time t at 0, right? This means that the maximum occurs at the current time, so you have no gap. So the gap max is 0. You are at the maximum at time t. What's the probability of that? Well, that's the probability that yt dominates all other values, right? All the previous tau values. And you can formalize this using this, the differences. So yt is above yt minus 1, yt is above yt minus 2, yt is above all of them. And you see, this is a function of the first differences of the process. And the probability of being in state 1 is the probability that the maximum is at time t minus 1. So again, you can score these probabilities from the properties of the process delta y, or of the vector of changes and lag changes, tau consecutive changes, and so on and so forth. And the transition matrix of this Markov chain is very simple. Perhaps we may look at the state transition diagram. So suppose that you are at the maximum at time t. What can happen is that the next observation, you are above this maximum. Then you are in state 0, so you are in the same state as before. You make a transition to the same state. Or, you leave the maximum behind because you are below the maximum, right? So in this case, you go to state 1. Suppose you are in state 1. What can happen is that from state 1, you can reach the maximum the next period of this run of values, and so you go back to 0. Or you leave the maximum behind if you don't go there. So you can go to state 2. From state 2, you can go to state 3 or go back to 0, and so on and so forth. That's the transition matrix we have shown here. It has this particular form where this upper diagonal thing is not empty, right? And this is when you return to 0 from any state. And then when you are you see, when you are in state tau, then the chain has to be resetted, right? So that's why you can go to any other state, right? And that's why you have all possible transitions here. Okay, so very elementary thing, and you can score these transition probabilities from the properties of the delta y's, again, right? So there is a nice and efficient way of doing this. Coming to the gap processes, then you have GT plus and GT minus. You can show that they are weakly stationary under the stated assumption that the delta y's are stationary with those properties. And you can work out the mean variance autocovariance function. I'm not getting into this. They are complicated formulas, perhaps not very nice to see. And as we have seen, you see these formulas are state dependent. They depend on the particular path that you are observing. But if you average out across all possible paths that you may observe, then you may characterize this as a filter. So you can look at the properties of this filter, which acts on the differences of the process. And you can work out the gain in the frequency domain and look at what the filter does and compare it to other filters. So for instance, you can show that the gain of the filter is this complicated expression, but not so much. And perhaps we better look at examples, right? So the key message is that you can derive the properties of these processes that are associated to YT. This is a very easy example. Suppose that your process is a Gaussian ARIMA with autoregressive order 1 and first differences and no moving average component. So then you see being a Gaussian process, you can score these probabilities and the properties of these quantities by the properties of the folded normal distribution, and you have analytical formulas for this. So for instance, the properties crucially depend. So think of the generating process like this, with 0.8 as the autoregressive coefficient, and suppose that tau, your forecast horizon, or your bandwidth is 5 days, 1 week of trading data, for instance. And a key element is the drift compared to the standard deviation of the normal, right? You can think of it of a Sharpe ratio or something like that. When this is 0, so you have no drift, you can work out the ergodic probabilities of being in state 0, 1, and so on and so forth. And I would like to point out that these probabilities are symmetric. So the probability of being in state 0 is the same as the probability of being in state 5, and there is a symmetry of the distribution. Another characteristic of this particular case, no drift, is that the same state probabilities, same state transition probabilities for state 0 and tau are the same. This is a property of the chain that we will exploit later on for reversibility. Now, this changes when you have a positive drift. When you have a positive drift, then you are more likely to be in state 0, close to the maximum, right? So that's the probability of being in, at the maximum at the current time, 0.67. And the probability of being, of observing the maximum 5 days ago, at time t minus 5 is much smaller, and you have a deviation from symmetry here, right? As you increase the drift compared to the sigma here, to the standard deviation, then these are more and more, the properties are, then you are most likely to be in state 0, and you are not likely to visit state 5, right? And so on and so forth. These properties are reversed symmetrically when you have a negative drift going down. You can work out the expectation, the variance, and the sort of the persistence of the gaps. This is a measure of how strong is the autocorrelation at lag 5, lag 10, and so forth. So these are analytically determined by the properties of the Gaussian distribution and the properties of the process. This is an application to US GDP, US quarterly GDP. Again, the series maximum and minima, you are very often at the maximum. These are the gap max and the gap mean. Gap max, you see, is very often 0, except at very deep recessions. And this is the gap mean, which is positive and high with respect to the other gap. So when you work out the output gaps, sorry, this is perhaps too much information here, but the output gap, which is the average of these two gaps once you have removed the mean, is the series in red. And you can compare it with other measures of the output gap that are very popular, such as the Baxter and King filter, which is this dotted line. And the Hamilton filter. The Hamilton filter I will not have time to explain, but it's a filter based on the residuals from the prediction of YT plus 8 quarters ahead, using the current and past values of output. So it's a residual from a prediction, is a sort of real-time estimate of the output gap. And you see it has more variability. It has an amplitude which is larger. This is a measure of deviation cycle, right? It's how much less you produce with respect to, the potential output, 5% less. In the Great Recession, you were producing something like minus 8% according to the Hamilton gap. You were performing below potential 5% less according to the output gap estimate in red. Now, that's the outcome, and you can see this as the outcome from filtering your time series. And the filter can be characterized in the frequency domain, as we sometimes do. As you may see, the gain is 0 at the 0 frequency, so you remove the low frequencies to some extent. And you can characterize the output gap filter, which is the gain is here in red, as a high-pass filter, right? It kills the long-run behavior, retains the components the cyclical component and the high-frequency component as well. That's the gain of the Hamilton filter for this particular case. This is a data-dependent filter because you estimate the coefficients of the predictor, but still, you can work out the gain. And as you see, it's above 1 that motivates why the amplitude is larger than this. And that's in green, you see the Baxter and King filter. That's the low-pass filter once you have removed that's a high-pass filter, sorry, once you have removed that's also a popular filter in economics. Okay, now estimation. Estimation is particularly easy. Method of moments estimates of the transition probabilities and the ergodic probabilities can be obtained by counting how many transitions you have in your sample and how many times you spend in one state. So I will not spend much time on it. And I go to the illustrations now. Time reversibility, yes. So time reversibility has been studied in stationary framework. So my definition is going to be a bit different because it's a conditional time reversibility. So here you see my definition. It's a bit elaborate. Perhaps I will illustrate it with a plot. So you see here you have a sort of a realization of a random walk without drift, but it turned out to be like this. Okay, suppose that this is your time series. You would like that paths like this have the same quotes probability as the ones that you get once you reverse, you look at the mirror image with respect to the vertical axis. And you want this to have the same properties probabilistically as when you look at the mirror image with respect to the horizontal axis, right? So that's the notion of reversibility, a condition on a point, and I say, oh, how likely am I to go up this way? Is it the same as going down this way or going down this way, and so forth, right? So that's the definition I have, and it's valid for non-stationary processes because I'm interested in the reversibility of asset prices and industrial production, for instance, rather than their stationary transformation. Now, it turns out that if you want to test this reversibility, you need to test that the vector of changes, delta yt minus 1 up to delta yt minus 2, is reversible at the same probability or the same CDF as the vector when you reverse the order of the observations. That's reversibility, right? You change the order of the observation. And furthermore, an additional thing is that the distribution must be centrally symmetric. It means that you take it with a minus sign, you have the same CDF again. So these are things that are difficult to test, right? Because they involve a multivariate joint distribution of the changes. But you can have an easy way to go about it if you look at the properties of the chain. So going back to the example, when the process is reversible, you have this feature that this is symmetric, this distribution is symmetric, and the same state probabilities are the same. So you can exploit this fact and base a test on a very simple things. So you count how many times, you look at the implications of reversibility, and you provide a test for that. Again, there's a lot of information. I don't want to go through it, but you see, you can use very simple things like compare how many times you were in state 0 and you are again in state 0, so the joint, an estimate of the joint probability of being in state 0, compare it to the joint probability of the estimated joint probability of being in state tau. You scale it by the long-run standard deviation of that, and you get an asymptotically normal standard test. So very easy stuff, I would say, very easy stuff. Now, when you do these things on output time series, you typically reject reversibility. Why? Well, because you see, when there is a drift, things are not reversible, right? When there is a positive drift, you spend more time in positive states than in negative states. Yes, 10 minutes, okay. But you see, when you account for that, and you look at, you remove the drift from the picture, right? Then things are more reversible. So output is reversible, excluding episodes like COVID, for instance. And financial time series are also reversible in this sense, excluding if you use a subsample that excludes the Great Recession and the COVID crisis. So that's the evidence that comes out here. But you get more reversibility than you expect in if you account that most of the rejections of reversibility is due to the drifting behavior of the series. Let me go quickly through other examples. One is estimating the output gap with a dimensional time series. Here we consider the 286 time series of industrial production for groups and subsectors of the US economy, monthly time series, and this is the breakdown of the series. They cover these sectors. What we do is the following. We score the output gap for each individual time series. That's a measurable transformation of the time series. It's like taking first differences, right? So we use a tau here, which is 2 years, a 2 years horizon. We choose 24 months because of we looked at the gain of what we obtain. So on frequency domain and cutoff notions that arguments, so frequency domain arguments. So we get our time series, and we estimate a factor model, and we capture the common dynamics. That's the basic idea. And I will not spend much time on this because it's fairly well known to most people, especially those who work in macroeconomics. I'm using the theory Fornilli P. et al. So I'm distilling from this 286 time series of output gaps of transform time series, I'm distilling the common component, right? By, say, generalized principal components, right? You know, there is a theory for that. Essentially, you estimate the cross-spectral density matrix of this time series, and then you look at the principal eigenvectors of this time series, and that defines the spectral density of the common component. From the spectral density, you retrieve the cross covariances by a process of Fourier inversion, and then you get the elements for the projection of the common component on the observable. That's the story, right? That's the story. Very simple story, so I won't spend too much time on this, and I will show you what comes out. So you have this common component, and now you can average that out. What weights do you take? Well, the weights that you take can be the weights that the Federal Reserve uses for aggregating this, or you can use a simple average, or there are several ways to go about this, right? So this is the variability that you get in the gaps, and this is when you aggregate the gaps using the common component only. So you remove the idiosyncratic things. You're not interested in things that pertain only to rubber or whatever other sector, right? And so you see it's a much smoother component. That's the kind of variability that you get. And we look at how important is the first generalized factor. The first factor is very important, right? It captures most of the interesting variability. You get information also from the other factors, especially for leads and lags with respect to it, or other strong movements in the series that can characterize. This is a measure of importance across the various sectors, so I'll skip this. Oops. Should I say okay? That's okay. And this is the variability of the output gap by industry group, so that's the overall gap for the industrial production, for the manufacturing sector, and then you have sector-specific gaps. Here is a comparison with other gaps that are popular. So for instance, the Hamilton gap, using always 24 as a bandwidth. And this is the real-time in black, the real-time Odrick and Prescott filter. And our estimate is a bit closer to the real-time output gap than Hamilton, perhaps, especially in sides. We perform a validation of this output gap. So in terms of forecasting, you can ask how important are these gaps? They are a construction. Are they relevant? They may be relevant for economic discussion, saying how deep is a recession in deviation form. And you can ask, do they contain important information for predicting industrial production? It turns out that they do. So we validate this in terms of predictive accuracy, several steps ahead for industrial production. And also for inflation. But for inflation, the results are, whatever you do, are very disappointing, right? But for industrial production, they contain relevant information. So we do something, I would say, standard in the literature in terms of predictability content of the output gap. And compared to the real-time Odrick and Prescott and other competitors, such as Hamilton and other ways of aggregating things, this is Cristiano Fitzgerald. We do pretty well in this case. So we are happy with this. That's about the sensitivity to the choice of tau. Yes, let me perhaps finish with this. Dating turning points, right? So this chain, ST plus, ST minus, are very useful because you can implement a dating algorithm on top of that. So what is a turning point? A turning point delimits phases, recessions, expansions, bear and bulls, and blah, blah, blah. And in particular, what is a candidate peak in a time series? Well, it's a time when you are at the maximum currently, so ST plus is equal to 0. That's the value of this chain. And you have been going up from the minimum. So the chain ST minus now, telling you the current lead time with respect to the minimum. That's a positive state. And that's, that's a positive state. You have been moving away from a minimum. You are at the maximum now, and then you are going down. So the next k values of the chain are j, right? St plus j is going to be j, because you are leaving j periods behind the maximum. So that's how you score a peak. And k acts as a duration sort of constraint, right? You don't want peaks to occur every day or so forth. You can do the same with a minimum. A minimum is a value at which you are currently at the minimum. You have been going down from a maximum. So before, the state here is positive. And after that, you're going up, right? You're going up. So you're moving up, and you're leaving j periods at time t plus j, the minimum. Now, that's all very well, easy to score. It's immediate. Now it's a two-sided filter, right? It's a two-sided filter acting on two variables, right? And so you have to look at also what came after to date this. Now, the only problem is that you now need to enforce the alternation of turning points. So you can locate two minima consecutive. So you have to look at the smallest between the two. That's all you need to do, right? So you enforce the alternation of turning points, and then this is what you get, for instance, for bear and bull phases in the Standard & Poor case. So you see here that's the trough that you find for the great financial crisis. And you see this minimum has been censored by the procedure, right? Because here I take an horizon of tau is equal to 65. 65 is a quarter of daily observations about, right? 3 months. That's the horizon, but the horizon is up to you, right? That's my investment horizon, say. And then you can delimit the phases, and you see that the white areas are much, broader than the gray areas, which delimit bare phases. Now, if you run this on the 500 components, then you can score a diffusion index, telling how many series are in a bare state. So that's a diffusion index, and as you see, when you have the Great Recession, then a lot of time series are in that state. So during a bear phase, you see that this diffusion index is above 0.5, and so on and so forth. Right, so 1 minute, okay. Now, you may want to predict these things, right? You may want to predict output gaps. These are persistent random variables that you have constructed. So you may pose the question, can I predict drawdowns, for instance? You see, drawdowns are persistent. They have an autocorrelation structure where that is very rich. They depend on lag differences. And so you can think of them as a nonlinear average of these lag differences, and so they are persistent. And what is the best way of predicting them? Should we, so let me just describe the last slide. Should we, so that's the drawdown that has been constructed using an horizon of a month here. That's the last of a span of a few observations, right? So how should I build my my forecast? I could use the drawdown itself, right, and model it. ARIMA models. I use the HAR model here, the heterogeneous autoregressive model, for instance. I use also term structure model for the drawdown and so forth, having the series itself. Or is it better to go back to the price time series, fit a model to the price, such as a Garch model, right, for the first differences, and look at the possible path and do something like particle filtering, and then score the paths that I get? And the answer is that, yeah, this particle Monte Carlo predictor outperforms all I can do, the best I could do on the drawdown itself. So that's just an application, but it shows that if you use the original process, you try to get the DGP of that process by some nice model that accounts for the volatility, which here is the main drivers, perhaps, of the drawdown. And then you are benefiting a lot. This is just one prediction in a period when you have a positive drawdown. This is the average or median, perhaps, prediction. That's the median prediction, and you get a 95% 95 credible interval for the prediction, and that turns out to provide a good predictor. So perhaps I will stop here. I had something about COVID, but actually I've lost my conclusions. It was this slide here. For some reason, it doesn't show. But the conclusion is that, there are interesting extensions like what you do when the process is seasonal. If the process is seasonal and regular, I mean monthly, for instance, then you can do every season at a time and score these things, which I did for instance, for the sea surface temperature of El Niño regions. What you do when you have outliers, max and mean are okay, but not sensible enough. They're sensitive to outliers. Can you use an order statistic that is different from that, and all this stuff? So these are the things that have to be looked after. Thank you very much for your attention. That's it.
Maybe we have time for one quick question, if any, otherwise Neil.
So have you considered, rather than rolling mins and max, historical to date min and max? And part of the interest here is this actually has shown up in the economics literature. It goes back to Pitterman looking at irreversibility and irreversible effects of inflation on asset holdings. And people always remember that they had high inflation in the past. So that might be quite interesting. And somewhat related to that, can you say anything about the mins and maxes, the rolling mins and maxes of a level or log of a variable versus the change in the variable? Because they will be fundamentally different. The turning points won't occur at the same point and so forth.
Coming to your second question, you mean the effect of the logarithmic transformation on max?
Not the logarithm so much, but the change. Because you could have an always upward sloping variable with different slopes, and the rolling max will always be the last observation.
Oh, yes.
But if you look at the change of the variable,
yeah, sure. Yes. So when you have such a run of values, then all the processes are no longer stationary, and then you can look at the differences and score the differences with these methods. Of course, this would fail. Also, in your first question, what happens if my tau is allowed to go to infinity in a sense, right? And that works for stationary processes, right? Or processes that have an attractor. They wouldn't work of processes that are drifting away, which is the topic of this talk. But yeah, of course you can apply this to stationary processes, and in that case, tau is something that you may allow to go to infinity in a sense, and you will always cross somewhere that enables you to delimit the maxima and the minimum. Yeah.
Okay, so maybe we can. I was wondering, well, I can take the advantage of being the chairman, about the real-time properties, because remember the output gap is not super well known for having a good real-time properties. If you remember papers by Orfanides and Van Orden, etc. Did you try with your filter?
Yes. So here everything is in real time.
Everything is in real time.
Yes, everything is in real time. So the output gap is observable at time t. Okay. It's a measurable transformation of what you have. So, but you may have it not real time. So you can have, imagine the following. You take your process, you score, you run it this way, and then you run it backwards, the same algorithm, and then you can average them out, and you get a two-sided output gap. But this is not real time, so it's subject to revision and so on and so forth. And so here you get zero revision, but it's like you run the Odrick and Prescott filter in real time, so you have zero revisions also there, right? So it's a property of what you do. So it's not necessarily a good thing that you don't have revision. It's just an assessment at time t on the basis of what you have, not looking at the future.
Okay, fantastic. Thanks a lot, Tommaso.
Thank you very much. Thanks.